today we're looking at managing resources. So when we're looking at virtualization infrastructure, we're talking about usually we're creating virtual machines and we're allocating the resources it can use. Like you're used to it with the fact that you can create VMware workstations, give it a certain amount of memory, disk space, number of CPUs or CPU cores. But that's fine. That's one aspect. That's just configuring the virtual hardware. The fact is, if you've got many virtual machines running on the same physical hardware like you have now for this subject, you can see that there's a lot of resource drain, right? Just because you give it 4 CPUs, just because you give it 16 gigs of RAM, doesn't mean you actually can get that much resources from the host computer, okay? Because that virtual hardware is just that, virtual hardware. But what resources can it give you, it depends on the situation at the point in time when it's requesting the resources. So today we're going to look at manage the VM memory allocation. We talked about the idea of virtual memory previously, and that's compared to physical memory. So do you guys know the difference between physical and virtual memory? Which one's better? Physical, yeah, that doesn't sound confident, though. Why is physical better? What's virtual memory? Guys, Solomon and Roman, you guys have done the
page file.
Yeah, that's right.
Last time.
That's right. That's why I'm testing you again.
Okay.
I'm testing you again. See if you remember what I talked about last time. Okay. So the page file, the swap, that's hard drive space, isn't it? So memory is RAM. Okay. Physical memory is RAM. Virtual memory is hard drive. That's why it's not actual memory. So we all know that RAM is fast. Physical hard drive, whether it's a hard disk drive that spins or solid state, which is a little bit better, but either way, they're a lot slower than the physical RAM. Okay? And so obviously, physical RAM is preferred for a virtual machine to run faster. But when the machine, the host, the physical machine host is under stress, meaning too many demands, if it doesn't have enough physical RAM, it will use the virtual RAM or virtual memory to give to the virtual machines. So therefore, when the virtual machine starts getting this virtual RAM, it doesn't know it's virtual RAM. It just thinks it's memory because the host obfuscates that. If you don't know what that means, it means it hides it. Okay? As far as the virtual machine is concerned, this is just RAM. But from the point of view of the host, this is actually virtual memory. So when it gets that, it's going to be the virtual machine is going to be very slow. So we're going to manage CPU utilization. We're going to create and manage what's called resource pools, and we're going to control network and storage I/O utilization. So before we get into all of the different types of ways we can control types of resources, we're going to talk about certain things which is going to be repetitive over and over again. Doesn't matter which resource it is: RAM, CPU, network, storage. We're going to talk about the idea of limits. We're going to talk about the idea of reservations. We're going to talk about the idea of shares, and all of those things can be applied to any resource. Doesn't matter if it's memory, network, hard drive, or even CPU. Okay, so let's have a look at a bit of an overview. Server virtualization allows us to allocate resources to VM based on its needs. In a traditional physical environment, a server is often provided with more resources than it really needs. Okay, so what does that mean? So when you buy a physical server, you don't buy for the minimum, you buy for the maximum, right? And your servers usually probably only maximum probably maybe 1% of the time. So 99% of the time you have more resources than you need. That's because physical machines are not flexible. If you want to add more memory, what do? You have to actually physically go buy memory, install the memory, and hopefully there's enough slots that you can actually add more memory. If you want more CPU, a lot of times your motherboard detects how many CPUs you can put in there. If you want more CPUs than the motherboard can cope with, then you probably have to even upgrade physical machine altogether. So that's why we over-provision. We put more in the physical servers than in the virtual. So even when you right size, that's a term, your VM, so right size is getting the size of the virtual machine correctly. So as you add more VMs, and each VM places additional demand on ESX host resources, at a certain point, the host will run out of resources. Like anything, right? You buy a big house, a 5-bedroom house, okay? And you suddenly have you got your own family, three kids. So you and the 3 kids, 4-bedroom. Then you have your mother-in-law come in. Then you have your sister-in-law maybe come to Australia, and you may need to just give them a temporary room. Even though you start off with a big house, eventually, if you keep on adding, you're going to run out of resources, right? So it doesn't matter. At any stage, it could run out of resources. What does ESXi do when it runs out of resources? That's the question. Okay, so we're not talking about the perfect world where there's plenty of resources to go around. We really worry about at that point when it runs out of resources. We need to understand what happens. By understanding what happens, then we can actually plan for what we can do to it. So how does ESXi handle it when VMs are asking for more resources than the physical host can actually provide? How can you guarantee that a guest operating system and its applications get the resources they need? So remember we talked about all these virtual machines? How can we guarantee that this mission critical VM is going to get the resources it need, but with these other VMs we don't care about, we don't care. You get me? So we've got like 20 VMs running on this host, but how can we guarantee that this mission critical one is going to get what it needs, whereas these other ones where we don't care, don't waste the resources on stuff that we don't care about. Okay? So that's the problems we're talking about. Okay, we're talking about the situation and that problem. So if we look at this picture again, it's a little bit outdated, but there's the idea of shares, reservations, and limits. Okay, and then there'll be another area for priorities as well. Sorry, shares is the priority. Sorry. So basically, these are the controls we can do. So with VMware vSphere, it offers a set of controls that guarantee access to resources when necessary to curb or control the use of resources, and we enable prioritized access to resources when available resources are low. vSphere offers 3 controls: reservations, limits, and shares. Okay, what's reservation? It's like you're reserving a table. It doesn't matter how busy the restaurant is. If you reserve the table, that means that's guaranteed to be yours. Okay, let's talk about memory for example. If we have 20 VMs, like I said, we've got some just plain silly little ones that we don't really care about. Let's say DHCP servers, like that's a virtual machine, but really DHCP server, is that priority? Of course, everyone needs an IP address, but is it a priority as far as resources goes? Not much, okay? But then we've got this web server, which is dealing with our customers where they can actually access and see our products. I would say, which is more priority? Probably the customer-facing virtual machine, correct? So how can we make sure that the customer-facing virtual machine gets their resource? We make reservations for a certain amount. Okay, what about limits? Well, what about that DHCP server? The DHCP server we created based on our template, if you remember. The template has virtual hardware. It says 4 gigs of RAM. But really, does this DHCP server need 4 gigs of RAM? Probably not all the time. Or maybe during installation of some things, yeah. But really, most of the time when you're running, really, you can just bring down. You guys might have noticed that that's what we did in our virtual machines for this class, right? Once we get it up and running, finish installing, we actually reduced the domain control. We reduced some of the other one. I can't remember which other one, but we can reduce those, and it doesn't make too much of a difference while it's running normally. So what we can do is actually set limits on those virtual machines, which we don't care about. Limits are a way to restrict the amount of given resource that the VM can use. The VM already has some limits, and that's by when we configure obviously the virtual hardware. If we say 4 gig, that is a limit already. But if we actually set the limit, if we allocate 4 gigs in the virtual hardware and we set a limit of 2 gigs, what does that mean? It means that after 2 gigs, that particular virtual machine will start using the virtual memory to get up to the 4 gigs. You see what happens there? So that's the one we don't care about. Whereas the one we do care about, we want to make sure the limit is not too low so that it doesn't use the virtual memory, for example, where possible. The next thing is shares. Shares is a priority. All right, let's put it this way. If 4 of us, okay, there's you all know about Powerball? Yes? Do you know about Powerball? Yeah, Powerball, the lottery, yeah? Yeah. All right, so there's Powerball tonight, right? We're going to bowl. Oh, you don't know, you don't care because you're a rich man. But let's. I know statistics. You know statistics is very low, but you could be lucky. Okay, that's what people think. Okay, I'm just using it as an example. Okay, the Powerball. So it says 20. It's 100 million tonight. Okay, there's 4 of us. All right, there's 4 of us, and we can buy a ticket for like what's it, 10 numbers, like a system pick, whatever it's called. I don't know what costs more. Let's say it costs $100. Okay. And if we all have equal share, you'll pay 25, 25, 25, 25, right? So when we win the $100 million, you would expect equal shares again, right? Yeah. You get 25, you get 25 million, I get 25 million, and Alexi doesn't care about statistics, so we can change his name, joking. But everyone gets the same amount, right? That's where everyone is equal. What if we have the same Powerball ticket, but we say instead of 4 shares, we say there's 10 shares. 10 shares, so it's $10 each. And let's say Roman says, I feel very lucky today, I'm going to buy 5 shares. Okay, so you pay $50. Someone says, I'm feeling average luck, so I'm going to buy 3 shares, 30 shares. Then Alexi says, you know what, I'm not even I don't care about this. This is not statistically not right. I'm buying 0 shares. And I'm going to buy the 20 shares. So when we win the 100 million, how much will you get? Oh, yeah, 50 million, right? Yeah, because you got the 50% of the shares. How much do you get? You get the 30 million, right? Because you got 30%. You get 0 million because you didn't buy any shares, and I get the 20 million because I only got 2 shares. You see how the shares does not have to be equal? Okay, you get me? So shares doesn't have to be always equal. Obviously, amongst friends, if you're doing something like that, you always have equal shares. But in reality, it doesn't have to be equal. So instead of talking about the Powerball, we're talking about humans now. We talk about the virtual machines. If we have 10 virtual machines, we have the DHCP server. We have the, what else is useless? The WSUS server, okay, that normally doesn't do much. Anyway, we've got the web server that's customer facing, and we've got the backend database, which the web server uses for the customer facing. Okay, so just in your mind, I'm trying to say that DHCP, the WSUS, not so important. The web server, database server, more important as far as business goes. Okay, so maybe instead of actually giving everyone equal shares to resources, we can give you 1 share. We can give you, because DHCP, WSUS is a little bit more, so I'll give you 3 shares. Web server, I might give him, 4 shares. And for me, let's see, how much is that now? Let's say 4 shares again, okay? So what does that mean? So you know that virtual machines are running all the time, resources are consumed, and we all are requesting resources. All right, so normally wherever resources available from the host are given out to the virtual machines. But let's just say a big virtual machine that was running, because the system was overloaded, the administrator has moved that virtual machine from this ESXi host to another one. So it had, let's say, 10 gigs of memory utilized. When it moves off this host, suddenly there's 10 gigs of memory available now, isn't there? For the rest of us. We all get 25%. Well, if we didn't have shares, we would. But if we had those shares, then again, you would get the amount of memory that's available now based on your shares. Your shares, your shares, my shares. So that shares is a priority access to how much resource becomes available. Okay, shares, it uses to establish priority. So So let's talk about memory. Memory is the easiest one to understand, so let's start with memory. When you create a new virtual machine, with the memory configuration indicates the amount of RAM the VM thinks that it has. Like I said, the virtual hardware, the virtual machine just thinks that it's all RAM. It doesn't matter what it is behind the scenes, it's all RAM. That's how much it thinks it has. What happens when you launch more virtual machines than you have memory to allocate? Will it run? Well, yeah, the answer is yes. The system will let you run. Let's say we've only got 10 gigs of RAM, and we've got 4 virtual machines, each computer with 4 gigs of RAM. That's 16 gigs altogether, isn't it? But we've only got 10 gigs of physical RAM, and we turn it all on. Will it run? Yes, it will run. How? So understanding ESXi's advanced memory technology. So what VMware ESXi is the only commercially available hypervisor on the market capable of perform memory over commitment in a manner that the guest OS is agnostic. What does that mean? Well, yeah, that means the guest OS doesn't know about it. Okay, so it's over committing memory, so it's giving the guests more memory than they actually have, but the guests are really not aware of it. Okay. VMware ESXi employs 4 different memory management technologies to make sure that the physical server's RAM is utilized as efficiently as possible. Okay, there's transparent page sharing, there's ballooning, there's swapping, and there's memory compression, and this PDF gives you more information about it. But let's actually talk about each one, okay? So transparent page sharing is where identical memory pages are shared amongst the VMs to reduce the total number of memory pages needed. Does this sound familiar? Something that you know of previously? Guys, does that sound familiar? What does it sound familiar to?
Linked quotes.
Link quotes? Sort of, no, not really. Anyone else want to guess what this sounds familiar to? I know you guys would have been taught this, but let's skip to it. Have you remembered data deduplication? Data dedupe? Remember that? That's in the file system where the data deduplication process looks for identical files, even if they're called different file names. They compare the bit level, and if they're the same, they store one copy and they reference it. Okay.
The same Office 365, it just suggests you to upload just one file and send the link to everyone.
Oh, that's the sharing of the files, but this is a data dedupe that doesn't even matter if all of us are different users. We all save to the same file server, and we store it into different areas. Okay. The same file, not the same file, it could even be called Roman's file, Alexi's file, Sol's files, and my file. And it doesn't matter what the file is called, where it's stored, but it goes through the whole file system and compares the files at the bit level. And if these 2 files are exactly the same, it just removes a copy, has one copy somewhere, and all of the other places where the file is used, doesn't matter if it's a different location, reference it. But when it changes, then it spawns off another copy with that location. Okay, that's called data deduplication. Okay.
Can it reference just to the part of the file? For example, if you have a big file, but 5 pages out.
No, it has to be the complete file. Okay. So it can't be partial. Okay, otherwise that's where you spawn off the separate files. So data deduplication runs through the file system and finds instances of this and removes duplicates. Okay, that's what deduplication means. But this transparent page sharing reminds me of that, because instead of looking at the file system, it's looking at memory. Okay, it's looking at sections on memory. If this section of memory and this section of memory are exactly the same, why store it twice? Okay, if you think about it, if we have 4 virtual machines running, and these are all 4 Windows Server 2019 virtual machines, do you think the stuff that we are storing in memory are going to be very similar? It's going to be different parts of the operating system, right? Different parts of the System 32 temporary files. So you can see if we're all the same operating system, a lot of the memory is going to be identical because it's all the same operating system, right? So this transparent page sharing is going to search for these identical parts and then just store it once. and let all the virtual machines access it. But the virtual machines are not aware of this. They just think that that's their copy, etc., etc. Okay? That make sense? Yeah, okay. Let's continue. The hypervisor computes hashes, so that's what it's comparing, the bit level. So if you don't know what a hash is, it's an algorithmic function that takes the bits and does an algorithmic function and ends up with an answer. If it does the same thing with this other part of memory and gets the same answer, that means they're identical. It's a bit like when you download a file, how do you know it's not been tampered with? You usually get a hash and then you check the hash, right? So that's what it does and identifies memory that's identical. If a hash match is found, a full comparison of the matching memory pages is made in order to exclude any false positives. So even though it's hashed exactly the same, they then do a deeper comparison. So the hash is a quick search, if you like, and then it does a deeper comparison and just make sure they are the same. Once the pages are confirmed to be identical, the hypervisor will transparently remap memory pages of the VM so they are sharing the same physical parts of the memory. So have you heard of the term transparent in IT before? Transparent proxy, transparent process. Have you heard of that term before?
Transparent proxy, yeah.
Yeah. So what do you think that transparent means?
Like almost invisible.
Yeah, a bit like that. Because when you use a transparent proxy, you don't even know you're using a proxy. You just send it to the gateway, and the gateway does its business, and you think you go into the internet, right? But behind the scenes, there's a proxy, and there's a cache, and all that kind of stuff. So when it's talking about transparent remapping, it means as the virtual machine doesn't even know about it. They don't care about it. They don't have to do anything about it. They just use it, and it's actually working behind the scenes like that for it. So ballooning, so there's another process. So any supported guest operating system can take advantage of all the ESXi memory management functionality. However, they operate with interaction from the guest OS. So this ballooning, so transparent paging operates independently from the guest OS because it's transparent, doesn't even know, but ballooning does not. So what the hell is ballooning? It says balloon. What do you think balloons do? When you blow in it, they go bigger, right? When you don't blow in or you release it, it goes smaller. So it's called ballooning because it expands and it contracts. Okay. So what ballooning does is actually involves the use of a driver installed inside the guest operating system. It's part of the VMware tools that we install into a guest operating system. Okay. The driver is part of VMware tools, and once it's installed in the guest operating system, the balloon driver can respond to commands from the hypervisor to reclaim memory from that particular guest OS. So what does that mean? So you guys are virtual machines, okay? You're using 4 gigs of RAM, 4 gigs of RAM, 4 gigs of RAM, and the hypervisor, ESXi, is going to turn on a new virtual machine, and they need 4 gigs of RAM reserved. Okay, that means there has to be guaranteed physical RAM. The hypervisor only has 1 gig of physical RAM available. So what does it do? It sends a signal to you, to Sol, to Alexi, and say, I need what's the 1 gig back? So it's like, I'm lending you money, I want like I lent you $300, I want $100 back now. Okay? So the hypervisor is going, all of you guys, and asking for memory back. So what does it do? So the machine can't suddenly give it back to you. Like, look, what was it going to do with all the the things stored in memory? So what it does is that balloon file, it's virtual memory, okay? That balloon file, the virtual machine starts, the VMware tool driver starts putting what's in physical memory into this balloon file. Okay, as far as the virtual machine goes, guest operating system goes, it doesn't know about it, but it's happening behind the scenes. So it's got to take 1 gig of your what's in memory, put it into this balloon, so it expands. Same with you, then frees up 1 gig each, and the host now has 3 gigs in total from you guys, and 1 gig you had already, and now on the new virtual machine, I get all this memory RAM for me because I've got that reservation. So this ballooning allows the host to sort of manipulate the RAM as it needs it. Okay? Make sense, that explanation? Okay, as long as it makes sense. So, once installed, the guest operating system, into the guest operating system, the balloon driver can respond to commands from the hypervisor to reclaim that memory. So when it asks for it back, it does this by requesting the memory from the guest OS, a process called inflating. So remember blowing up the balloon, and then passing the memory back to the hypervisor for the use for other virtual machines. Swapping. Okay, swapping, that sounds like that memory Linux thing, isn't it? Virtual memory. There are two forms of swapping. There's guest swapping, guest OS swapping, which is in which the guest operating system, the VM swap pages out to its virtual disk according to its own memory management. So if you've got a Linux or virtual machine, for example, it just puts in the swap partition. You've got a Windows one and puts in the page file. That's what the guest operating, that's what a normal operating system does anyway. Okay, so that's not really what we're talking about. Okay, that is just normal functions of the operating system. That's not what we're talking about as far as what we're interested in. Hypervisor swapping means that the ESXi is going to swap memory pages out to disk. So remember, physical RAM is good. Hard drive or SSD even is bad, slow. So swapping means taking some of this out of the physical RAM and putting on the SSD or hard drive. Okay, so it does this in order to reclaim memory that is needed elsewhere. So let's say there's a demand, increased demand elsewhere. So like I said, these actions only take place when there's not enough resources. ESXi swapping takes place without any regards to whether the pages are being actively used or by the guest OS. What does that mean? It means that if you are a virtual machine enrollment and you're using this stuff in memory, you're like busily doing your work, and me as the ESXi, I'm just going to say, yeah. So it's like almost like I don't care. It's almost like even though you're busily using this, I'm just going to put it in the virtual memory, and you have no choice. Okay, what does that mean for you? It means you're suddenly going to slow down dramatically. Okay. As a result, the guest OS performance is severely impacted if the hypervisor swapping is invoked, because normally, if it's actively using, the guest OS wouldn't put it into swap. It would just keep it into physical memory. This is why ESXi won't invoke swapping unless it is absolutely necessary. It's one of the last things it does. Okay. The key thing to remember about hypervisor swapping is that you want to avoid it if at all possible. Okay. This is the worst. If you do it, it's going to suffer. Performance is going to suffer the worst. Okay, then there's memory compression. When ESXi host gets to the point that the hypervisor swapping is necessary, so this is after you realize you need to do the hypervisor swapping, the VM kernel will also attempt to compress memory pages to keep them in RAM in a compressed memory cache instead of swapping. So what do we know about compression? So we all zip files before. Okay, so is the performance of accessing those zip files faster or slower? Slower, that's right. Every time, if we're working with compressed files, every time we need to write to the files and save, we need to compress it. Every time we need to read and modify the files, we've got to decompress it. So that's CPU power. That's lag as far as responsiveness. Okay, so memory compression is the same. It's every time you have to compress it, you have to go compress it, and every time you have to use it, you have to decompress it. All right, pages that are successfully compressed by at least 50% are put into the compressed memory cache instead of being written to the disk, and then can be recovered more quickly. So even though it's saying the compression is slower, nice will slow the swap. That's what it's saying, okay? Memory compression can dramatically reduce the number of pages it must be swapped to disk, and thus dramatically improving the performance of the ESXi that is under strong memory pressure, like where it's really in high demand. Compression is only invoked when ESXi host reaches the point where it needs to do that hypervisor swapping. So hypervisor swapping is the last resort, but this memory compression is going to try to relieve that as much as possible. Okay? But still not ideal, but better than swapping. Controlling memory allocation. So we're using memory reservations. So like I said, reserving a table guarantees you a certain amount of RAM. The default memory reservation is 0, or no memory reservation at all. So if you do nothing, it means that that virtual machine, the RAM, could all be virtual at some stage, potentially. The memory reservation amount specifies that on the resource table of the virtual machine settings is the amount of actual physical RAM, okay? Not the swap or .virtual RAM or anything like that. This is guaranteed how much physical RAM it has access to. A VM with a memory reservation is guaranteed that amount of RAM configured in the reservation setting. So obviously, where would we do it? We would do it for the very high value critical virtual machines. For the low value, probably configure no reservations at all. Okay. So here's a example. So in this case, the memory reservation is actually set to 1 gig. Okay. Oops. Set to 1 gig. Yeah, don't worry about everything else, the limits or the shares. Set to 1 gig. So what does that mean? If this virtual machine is turned on, it needs 4 gigs. It's actually, I think the virtual hardware is configured with 4 gigs. So if it needs all 4 gigs, it means that this first 1 gig must be in RAM, but these other 3 gigs, if the host has plenty of RAM, no problems, it will be physical RAM. But if the host doesn't have enough RAM, then these will be part of the hypervisor swap file, the virtual memory. What about limits? By default, all new VMs created without a limit, so there's no limit, which means that the initial RAM you assign to it during creation is effectively the limit. What does that mean? The virtual hardware, where you say it's got whatever RAM, that's the limit. But, so what's the point of the limit then? So it's already got a limit from the virtual hardware. What's the point of limit? It sets the actual limit on how much physical RAM. Okay, when you create the virtual hardware, you say 4 gigs. That is a limit if there's a limited RAM on the host, or if there's plenty of RAM. But if there's not enough RAM, this setting means that this virtual machine will never use more than 1 gig. Let's say if it's 1 gig of RAM. It sets the actual limit on how much physical RAM that the VM might use. When this limit is reached, the balloon driver, like we talked about before, kicks in and prevents the OS from using any more physical RAM. When the guest OS memory demands drops below, the balloon driver deflates and returns the memory to the guest. Okay? So the guest OS is not aware of this. It just happens behind the scenes. And unfortunately, the performance suffers. But we would only put limits or lower limits on machines that we don't care about. Memory shares. The share system in a VM where is a proportional share. Systems that provide administrators with the means of assigning resource priority to VMs, but shares are only used when ESXi host is experiencing physical RAM contention. That's when there's not enough. Again, if there's plenty, no one cares. We're talking about the situation where there's not enough. Okay? So in other words, if 2 VMs want more memory than their reservation limits, and the ESXi host can't satisfy both of them, so let's say both of you guys, you both want RAM. But I don't have enough for everyone. What do I do? Okay? So it can't satisfy both of them, then you can set a share value to each VM so that one gets higher priority to RAM in the ESXi host than another. Okay, so let's say Robin and Alexi. Okay, you both want RAM. but we'll give you different shares. Okay, so you have 2 VMs, Roman and Alexi, with 1 gig reservation each, so you guarantee 1 gig of physical RAM, but you have a maximum 4 gigs, so you've got 3 gigs somewhere. Okay, so obviously if it's not physical, it could be virtual. All right, both are running ESXi hosts with less than 2 gigs of RAM available to the VMs. So if the 2 VMs in question have an equal number of shares, so if you both have 1,000 shares, it's equal. So you both get whatever 50-50 share of whatever I got. Okay. Then each VM requests memory above its reservation value will receive an equal amount of RAM. But furthermore, because the host cannot supply all of the RAM for both, each VM will swap equally as well. So if you've got the same shares, you have same access to RAM, but also same access to the virtual memory. Okay, so no one's got high priority there. But what if I decide that Roman, I like him better? Okay, so I'm going to give him slightly higher shares. So I'm going to give him 2,000 shares. You stay 1,000. So total is 3,000, isn't it? So it's not about the number, 1,000, 2,000, 6,000, whatever. It's what the total is. Okay, in this situation, total is 3,000. So Roman has 2,000, so he gets 2/3, and Alexi only gets 1/3. But what if I give him 4,000 shares and you give him 1,000 shares? Now the total is like 5,000, isn't it? In this case, he would get 80%, and you would get 20%. You see how the number doesn't really matter. You can do 1, 2, but because you say thousands, this gives you more fine-grained control. All right, so to do with the total. So if we have the 1,000 like in the first instance, both get 50% because the total is 2,000. 1,000 shares is 50%, right? So in the second instance, Roman gets 2,000 and Alexi gets 1,000. So Roman gets 2/3 and Alexi gets 1/3. And I'm sure you guys will understand. It's not a big deal. So now if we have, now we have 3 VMs. Now Son's joined the party. Okay, so Son has 1,000 shares, and Roman has 1,500, and Alexi has 1,500. So there's 4,000 shares. So that means Son, with his 1,000 out of 4,000, 25%. Roman, 1,500 out of 4,000 is 37.5%, etc. Okay, so it's all a percentage based on the number of shares you have over the total number of shares. Okay, I think maths is pretty easy for you guys. No need to explain anymore. And trust me, in the cert for some students really not good at maths. When I teach you that, what you have a question or you have no good at maths?
Not about math.
Yeah.
So normally we allocate like in thousands.
Yeah.
Not in, because for me it's easier to allocate just in hundreds. So you have like 100.
Yeah.
And you just distribute these.
Yeah, like I said, it doesn't even matter if you allocate in ones or twos. The fact is, when you allocate in ones or twos, there's no such thing as 1.5, is there? Okay. So when you have the bigger the number, the more finer control you can have. Okay. Yeah, there's no decimal places.
Yeah, but I suppose there might be a problem. For example, you distributed like 50% and 50%, and then you're adding the third virtual machine.
Yeah.
So if you in your mind have to like equal share, you have to reduce on these two machines and then add to this.
No, you don't have to, because you just add.
You just add in like extending the pool like providing extra.
Now instead of out of 2, it's out of 3.
Yeah.
Yeah. So that's what I'm saying. The total number. It's a percentage of your share over the total number. Okay. So it doesn't matter. That's the whole beauty of it. You don't always have to think in 100%. Okay. You just give them 1,000, give them 1,000, give them 2,000. Then if it's 4,000, you get 50%, they get 25% each.
Okay.
Okay. But if I decide you've got more priority, I say give me 3,000, and these guys still have 1,000. Now you get 60%, and these guys get 20% each.
And in the GUI, when you distributing these extra shares, do you see like how many shares right now you have, and how many other hosts have like tables?
You can actually find it, but it's not going to give you a total at that point, okay? So you just have to look at what the total is. And I think that's the beauty of it, because I don't have to worry about what the 100% is, because we're moving virtual machines here, there, everywhere.
Because you don't know whether it's hundreds, thousands, or tens of thousands.
Oh, well, you would have a sort of, what do you call it, a convention. In my organization, we're going to do in thousands. Okay, so whatever share you have has to be in the thousands. Okay, so whether it's 1,500 or 900, your share is 900. I don't know why it's 900, but if it's 900, that means you're below 1,000, but the whole thing is in like in the thousands. Okay, so if I give you 900, there must be a reason, because I want you to have even lower priority. Okay. So, but the beauty of this is you don't have to try to calculate. You just set 1,000, 1,000, 1,000, 6,000. And it will do all the calculations for you behind the scenes, okay? Because if you have to always worry about the 100%, what if you add another virtual machine in? It's going to be 150%. You know what I mean? But if I add another virtual machine in, it's still got shares from configured previously. If it gets on here, it just adds the shares to the total and then gets percentage based on that. Okay?
But at least, can you see the percentage when you allocate the share?
No, you can't see the percentage. Okay. You just basically see, where is it? Here. Okay, the shares, there's normal, high, but we can then actually get fine-grained and use the number here. Okay? So you can have just like low, normal, high, just basic ones. Or if we want to be more fine-grained, we configure a number here.
Yeah.
Okay? So, yeah, let's keep on going. So summary, memory summary that is. Reservations guarantee the memory for a particular VM. Memory is allocated until requested by the VM, but the host must have enough free memory to satisfy the entire reservation. You cannot reserve more memory than the host has. So if your virtual machine you want is reserve 16 gigs, but your host has only got 12 gigs, you can't do that. You can't be on that host, basically. Once allocated to the virtual machine, reserved memory is not shared, swapped, or reclaimed. It means it's got it. It's just got it. You can't take it away, okay? Because it's reserved. Limits enforce the upper ceiling, the maximum physical RAM. Limits is enforced by using the balloon driver. So if it gets above the limit, then the driver inflates. And as the OS needs less, it deflates. Okay? As the VM approaches the limit, the balloon driver will inflate to keep the virtual VM memory usage under the limit. This will cause the OS to swap out to disk, which is typically very slow and degrades the performance. Shares apply only during periods of host RAM contention. Like I said, shares make no difference if there's more than enough. It's only when you don't have enough that the shares or priority comes into hand. So VMs are granted priority based on the percentage of the shares allocated versus the total shares granted. Okay. So what about CPU? So CPU is a little bit more complicated because memory is a set number, isn't it? You've got 16 gigs and you allocate this much and this much and this much. It's pretty easy to understand. CPU is cycles per second, isn't it? How many cycles per second? If it's 3 gigahertz, it's 3 million or 3,000 million hertz per second. Okay, that's 3,000 million, 3 billion, if you like, cycles per second. Okay, so how many CPUs should a VM have? The VM kernel simultaneously schedule CPU cycles for multi-virtual CPU VMs. This means that when you have when a dual virtual CPU VM places a request for CPU cycles, the request goes into a queue on the host, and the host waits until there are at least 2 cores or hyperthreads with concurrent cycles to be scheduled to schedule that VM. Easy to understand or hard to understand that question? So let's put a simplifier. If I allocate 2 cores to a virtual machine, it needs a cycle. It needs to do some processing. It will say, I need CPU cycles. The host now will look at its physical CPU, and now it has to find 2 cores or 2 hyperthreads that's free at exactly the same time, and then give it to the virtual machine. So if you think about it, like I said before, is it easy when you go to a restaurant to look for a table for 10, or is it easy to go to a restaurant for a table for 2? Which is easier? 2. Yeah, 2. I can squeeze in 2 in. If I've got like 20 seats in the restaurant, I can squeeze 2 people in very easily, right? But can I squeeze 10 people in? Not so easy. So therefore, if you configure your virtual machines with too many cores, like if we got like one CPU like on our system quad core, and we configure a virtual machine with quad core, then we'll have to wait for all 4 cores of the physical CPU to be free before the virtual machine gets a turn. Get me? It's very hard. Very low possibility, isn't it? Like you said, Mr. Statistics, it's a very low possibility of that happening. So it actually degrades the performance of the virtual machines. So actually allocating the right amount of CPU cores is actually better. Because if you got 4 cores and you allocate maybe maximum 2, it's more easier. So this occurs even if the VM needs only a few clock cycles to do some menial tasks that should be done, that could be done on a single process. So in this case, instead of having 2, have a single process, you get it done very fast, a lot faster. On the other hand, if a VM needs 2 virtual CPUs because of the load, it will be processing on a constant basis. So you have to depend what is the virtual machine doing. Is it just doing a DHCP? Why do we need so many CPU cycles, right? It's doing heavy processing because it's a database server and there's multiple queries and reports generated from the server from many users. It needs those CPU cycles. All right, so on the other hand, if a virtual machine needs 2 virtual CPUs because of load, it will be processing as a constant basis, then it makes sense to give it 2 virtual CPU, but only if the host has 4 or more. If the host only has 2, then it's very low likelihood that you'll get both of them free. If your ESXi host is an older generation, dual processor or single core system, then assigning VM's 2 virtual CPUs will mean that that VM owns all of the CPU processing power on that host every time it runs a cycle. So these things are there to consider. I know this is like, this is talking about 1, 2, obviously we're used to now 4, 16, whatever, 32 cores. But still, it applies the same reasoning when you're allocating how many cores. If I've got a 32 core system as a host, then I shouldn't be allocating 32 cores to the virtual machine, right? So it's the same philosophy. All right, so if we're talking about CPU now, we've got the shares, we've got the reservations, and we've still got the limits, but this is now is in megahertz. The shares, sorry, not the shares, the reservation and the limits. So remember, we talked about the gigahertz CPU, how many cycles per second. So if we're putting a limit or reservation, it's in those hertz. Okay, it's in the megahertz. Oh, sorry, I think I missed the thing. Where a new VM is created a single virtual CPU, or with a single virtual CPU, total maximum CPU cycles for that VM equals the clock speed of the host. So basically, if you just create a new virtual machine, it's going to use the maximum. Okay, that's it. So unless you put a limit on it, it's going to just use the maximum wherever it can, or wherever it needs it. This is a interesting one. I wouldn't recommend it, but this is possible. You can set CPU affinity. Okay, what does the word affinity mean? Yeah, just the English word. I know we're all here in this room, even me, English is our second language, okay? So that's why I always check, what does this weird word mean, affinity? Ever heard of it before? No? Okay, that's good, because then I can explain it to you. So affinity means I like. I have an affinity for badminton because I like badminton. Okay? CPU affinity means this virtual machine wants to be with that CPU. So why would people do this? So if I've got 4 CPUs and there's 4 virtual machines, if I just actually make this virtual machine have affinity to this CPU, this virtual machine with affinity to this CPU, this virtual machine affinity with this CPU, it's almost like each virtual machine can have its own CPU, right? That's what the theory is, okay? So in addition to shares, reservations, and limits, vSphere offers the 4-hop option for CPUs, and CPU affinity allows the administrator to statically associate a virtual machine with a specific CPU or CPU core. Like I said, I would recommend this. So CPU affinity is generally not recommended. It has a list of rather significant drawbacks. So there's some benefits. It's got a dedicated CPU or CPU core. But the limitations is that you can't move the virtual machine. Because if that virtual machine is being configured to work with this CPU, you can't move it because it's not going to work with any other CPU, right? So it breaks the immersion. The hypervisor is unable to load balance the VM across the processing cores on the server. So what does that mean? If I've got 4 CPUs and there's 4 virtual machines each having affinity to a different CPU, let's say Alexi is a virtual machine and he's got affinity to this CPU. Now he becomes very, very busy. You guys are not so busy. I'm not busy. But because he's only got affinity to 1 CPU core, even though these other 3 CPU cores are free, he's never going to use them. You get me? So it's like, it's like you are going to a work site and there's one person busy, but no one else is allowed to help him. You know what I mean? All right. So because vMotion is broken, you cannot use CPU affinity in a cluster where you use the distributed resource scheduler that isn't set to manual operation. Because of these limitations, most organizations don't care about this. I wouldn't recommend it. It's possible. If you have a static system, like a very small system, and you want to do something fancy because you're doing like a lot of number crunching, and you know that these 4 virtual machines always have equal load, and you can do this. But not many situations where you would do that. Okay, CPU reservations. The default CPU reservation is 0. Okay, no reservation. Therefore, by default, VMs are not guaranteed any CPU activity at all. This means that the VM will work. This means when the VM has work to be done, it places its CPU request in the CPU queue, and the VM kernel, which is the host operating system, if you like to think of it, will handle the request in a sequence along with other requests. It's just a line. You line up, you get your turn. On a lightly loaded, so on an ESXi host with not much load, not a problem. They just get the turn and everyone's happy. But the problem is always when there's not enough, when it's very busy or it's high demand. So on an ESXi host with not much load, it wouldn't have to wait too long. However, on a very heavy loaded host, the time this virtual machine might have to wait could be significant because it's very busy. The ESXi must be able to satisfy the reservations by providing each enough resources to meet the reservation. If each VM creates a 1 gigahertz, basically, reservation, your host has 12,000 or 12 gigahertz CPU capacity. You cannot power any more than 11. So you can't actually turn on any more after that point. You can't have reservations that you can't meet, basically. It's just like me saying, your restaurant can only seat 20 people. You can't take a booking for, once you get 20 people in the restaurant, you can't just tell someone, squeeze someone else in, can you? You're done. They have to wait outside. It can't be started at all. Reserve memory cache. Reserve memory, once allocated to a VM, is never reclaimed. So when we're talking about memory, once it's allocated to reserve memory, it's never reclaimed or shared in any way. but the CPU is not true. Because memory is a set amount, isn't it? Storage. You're storing something, it's always in there, and you always have it. But the CPU cycles, it's like the wind. If you don't use it, it's gone, isn't it? So if the cycle, if no one's using it, it's gone. So suppose you have a VM1, has a CPU reservation of 1 gigahertz. If the VM1 is idle, or nothing, then the reserve CPU cycles, those cycles can be given to another VM, because if you're not using it, then it's going to be wasted. So it can actually be used by other VMs at that point in time. So if VM1 suddenly needs the cycles, then VM2 doesn't get any more, and they are, because they're reserved, they're given back to VM1. CPU limits. This effectively limits the VM's ability to see the maximum number of clock cycles. So basically, it's dangerous to do this, to do a limit, because even if it's not busy, even if the host is not busy, your virtual machine will never see more than that, those cycles. The drawback is using CPU limits is that the performance impact will have on the guest OS and the applications running on it. The limit setting is a true limit. The VM will be scheduled to run on a physical CPU core more than the limit specifies. You're basically preventing them using any other free cycles. It's important, therefore, to understand that the CPU processing needs of your VMs before you arbitrarily set limits. I wouldn't set limits on the VMs unless I know for a very, very good reason. Okay? Because, like I said, it means that even if the CPU is 100% free, your virtual machine that has a limit will never use those free cycles. So CPU shares, same idea with the shares, it's a percentage. The shares of CPU will determine how much CPU is provided to a VM in the face of contention. So contention means when there's competition with other virtual machines needing CPU activity. All VMs by default start with an equal number of shares, which means that if there's competition for CPU cycles, the ESXi host, each VM will get the same priority. If there's no CPU contention, the host has plenty of cycles to go around. The CPU shares has no effect. So summary, reservation set the cycles set on the CPU cycle guarantees processing power for VMs. Unlike the memory, if the CPU cycles are not used by one, it will be given to others. The ESXi host must have enough real physical CPU capacity to service all the reservations before it allows you to turn on any more. You cannot reserve more CPU cycles than the host actually has. Limits on the CPU usage simply prevents VMs from gaining access to additional CPU cycles, even if they have plenty. Shares are a priority only when there's competition. Okay. Resource pools. So we've been talking about all the resources on the host now, okay? And then all the virtual machines fighting each other for all the resources. Resource pools now is an object in the vSphere. We create a resource pool. We allocate how much resources are in this pool. It's almost like we're taking our resource, we're dividing it into small amounts. We create a pool, we give it resources, and then we put virtual machines inside this resource pool, and then the virtual machines inside the resource pool will fight for the resources that is being allocated to that pool. We could have a low priority pool, for example, the DHCP server, the WSUS server, and I'll give you a certain amount of resources, and you guys can be there. You can fight each other for those resources. But whatever resources that's not given to these ones are left over, you cannot access. And then I'd create another pool for the high priority VMs, give them more resources, whatever, and then the virtual machines in there will utilize that. You can use resource pools to make the allocation of resources to a collection of virtual machines. So instead of treating virtual machines one at a time, we can do it in a group. In other words, instead of configuring reservations, limits, or shares per virtual machine, you can use the resource pool for those values to give the virtual machines all at once. A resource pool is a special type of container object, much like a folder. If you examine the properties, you'll see there's CPU settings like reservations, shares, limits, etc. And another section similar to the settings for the memory. When you apply a resource setting to a resource pool, those settings affect all VMs in that pool. So let's have a look at managing CPU usage with resource pools. So 2 resource pools. We've got production and we've got development. So if you don't know what that means, production is the virtual machine that's servicing the clients, providing the service to the real clients. Whereas development is where you're sort of testing. Okay? So 2 resource pools with different share values. So you can see that production one has 8,000 shares, and the development pool has 2,000 shares, which makes the total 10,000, isn't it? So that means that the production really is going to get 80%, and the development is going to get 20%. So 2 resource pools with different share values will be allocated a resource to be allocated a resource proportional to their percentage of ownership. There are only 2 resource pools under the given ESXi host, and CPU will be allocated 80-20. So 80% production, 20% to the development. So now, so this is going to get, let's make it easy to understand, okay? Let's say there's 10 gigs of RAM. Oh, sorry. No, let's talk about 100% CPU cycle, okay? So production is going to get 80% of the CPU cycles, but then there's 2 virtual machines within that production CPU, production pool, and they've got 1,000 shares each. You can see they're equal, aren't they? So now they will get 50% of whatever this resource pool got. So if you want to think about it, they get 50% of the 80%, which is 40% each for the total resource, CPU resources. You get me? Understanding that? Okay. And this one gets 20% for this pool, but each VM is 1,000 shares as well. But these are 1,000 shares that are compared to each other, not to these ones, because they're in different pools. So they get 50% of this pool, which is 50% of 20%, which is 10% of the actual total. Okay, easy to understand. Memory resources, the share values system works in the same way for memory shares work on individual machines. It determines which group of virtual machines will be first to give up memory by the balloon drivers. However, this setting is used to set the priorities value for all VMs in a resource pool when competing for resources with VMs in other pools. The memory reservation value will reserve the amount of RAM for the VMs in this resource pool, and the memory limit is how you will set limit on how much RAM this particular group will consume. So really, these resource pools is a way of configuring resource management for groups of virtual machines. All right. What about network I/O? So if you for memory is easy to understand, just number. CPU is a percentage of CPU cycles. The network I/O is the input-output operations. Okay? Input-output operations. How many I/Os do each virtual machine get? So network resource pool allows you to control network utilization. Using network resource pools, you can control outgoing network traffic. This feature is referred to as vSphere Network I/O. So it's Net IOC. Okay. And when you enable vSphere Net IOC, vSphere activates 6 predefined network resource pools. There's a fault tolerance traffic, iSCSI traffic, management traffic, NFS traffic, virtual machine traffic, vMotion traffic. These are predefined pools. They're really crazy. So a network resource pool consists of 3 basic settings. There's a physical adapter shares. So physical adapter shares in a network resource pool establish the priority for access to the network adapter when there's a network contention, so when there's competition. There's host limits. Okay, this is easier to understand. host limits is what's the limit of each host. So this is like when you throttle an internet connection, you're limiting how fast your internet is going. So this one we can actually do in megabits per second. Let's say that the HTTP server again, low priority. We might restrict you to maybe 10 megabits per second, even though we've got a gigabit link. And for the W stuff, we might give you 20 megabits per second. Okay, but for the web server, maybe we're given like no limits at all. Okay. So the quality of service priority tag is a 802.1p tag. So you guys have learned about quality of service in your Cisco, right? So that's a tag that then the Cisco devices recognize and give high priority to it in the traffic. So if our host is capable of putting this tag on, that means all across the network, the upstream network switches are also configured to recognize these tags, which further enhances the enforcement of the quality of service. Okay, regulating network utilization in a large environment with lots of port groups, it might be a bit tedious to try to determine which port group are mapped to which network resource. So yeah, it might take a long time. So what we can actually do is actually use this network resource pools and look at the port groups here and look at if it's enabled and how many ports. Then there's the storage. The storage is storage IO as well, input output request. So other workloads will present on the shared storage that is required by vSphere for so many features. These other workloads are going to be external. So what does that mean? If I've got a SAN, my ESXi hosts are connected to it. That's fine. And that's what we can control. But what about the file server that's connecting to the SAN? What about the other servers or clients who's connecting to the SAN? They're outside of the control of this. That's what it's saying, external workloads. Because we can only control our virtual machine's interaction with the SAN or the storage, but we can't control other interactions to the SAN. All right, there are other workloads. It's going to be external, and they cannot be controlled or influenced by vSphere at all. But they're still going to have an effect on the performance. It is also generally true that the hypervisor won't have much visibility into the network storage, into the storage, as it does with the CPU memory, making it more difficult to detect and adjust the utilization. Because we've got shared storage, the hypervisor does not control it. The hypervisor only uses it. Whereas the CPU, the memory, the network, all part of the hypervisor hardware, isn't it? So it has more control. There's a metric, however. Metric is something you can measure that vSphere can use to help determine the utilization of storage. The metric is latency. If you've never heard of that term, it's lag. Okay, it's another word for lag. Using latency as the metric to detect contention, vSphere can offer shares as well as limits. This feature that enables this functionality is called storage IO control, or SIOC. SIOC, all data stores that are SIOC enabled have to be under the management of the single vCenter server instance. SIOC is supported on VMFS data stores and connected via fiber channel over Ethernet, or iSCSI. NFS data stores are also supported, but raw device mappings are not supported. Let's have a quick look at where we're at. We're nearly finished. I thought we were going a little bit longer. Sorry. We started a little bit late too. So configuring storage resource settings for virtual machines, SIOC provides two mechanisms for controlling the use of IO by VMs. Shares, which we already understand, gives you relative priority or ratio. Limits defines the upper ceiling, the number of IO operations per second. It's almost like how we talk about the IOPS for SSDs. It's almost like limiting how many IOs per second you see or can use. All right, so that's the end of the thing, and you'll see in our worksheet and also your assignment, the most important things are the CPU and RAM. Okay, the other stuff are here and there, but not so important. The RAM is probably the most important because that's the one where you, once you give it, you can't take back easily. Whereas the CPU, yeah, I'll give it, but if not using it, I can still give it to someone else. And same with the network and our storage, really.